This whole video pretty much I'm just talking about how a photoreceptor's ability to interpret light via using a few other cell types, specifically bipolar and ganglion cells. So the way I have my layout, we have on the right the layers of the retina, and in the middle we have a photoreceptor at the very top, followed by two bipolar cells. One of them with the squares is an off-center bipolar cell. The triangles is an on-center, and the double square at the bottom is an off-center ganglion cell, and the double triangle is an on-center ganglion cell. So when a photoreceptor is activated or depolarized, and the depolarization happens through darkness, not through light, so when the photoreceptor does not see light, it becomes depolarized and releases glutamate, which I'm still drawing in orange from the other video, to both the on-center and the off-center bipolar cell. But the on-center and off-center bipolar cell interpret the presence of glutamate differently. The off-center bipolar cell will see the glutamate and depolarize its membrane, allowing an action potential to continue down to its axon terminal to release glutamate here as well. And the glutamate will then bind to the AMPA, kinatin, and NMDA channels on the off-center ganglion cell, allowing an action potential to fire down even further. This is in darkness. But you have darkness still, and you see glutamate and it binds to an on-center bipolar cell. This is going to interpret it a little differently. This is going to hyperpolarize the membrane due to a special receptor it has on its surface called mGlu-R6. And it sits up there. And because of that, it's a metallotropic receptor, and because of it, it hyperpolarizes the membrane, not allowing an action potential to follow through, which means that nothing's able to continue on through the on-center ganglion either. So that's how that works with darkness. But if we use the other example and we shine light on the photoreceptor, it means that this is no longer being depolarized, which makes it unable to release glutamate from its terminal. This lack of glutamate will go with the off-center so far. The lack of glutamate does not allow a depolarization event to occur in the off-center bipolar cell, which obviously does not allow it to create an action potential or to transmit the signal to the off-center ganglion. But when we see the on-center bipolar cell, because there is no glutamate, there is no inhibitory possibility for mGlu-R6 to affect the on-center bipolar cell. So what happens is, in its natural resting state, it is able, or without the inhibitory process of mGlu-R6, is able to send an action potential down to its axon terminal, and then use glutamate as well to then synapse on to the on-center ganglion cell. This of course happens just like it did for the off-center ganglion cell through the AMPA, kinatin, and NMDA channel. And this is how you're able to differentiate between light and darkness through a photoreceptor. Thank you.